Assalamualaikum and hi everyone. My name is Auni and right now I'll talk about the objective. The objective of doing this project is first to increase our knowledge about transformers, second be able to identify the transformer circuit and complete the calculation, third be able to identify transformer applications in the real world. Right now I'll talk about the background of the transformer. A transformer is a passive component that distributes electrical energy from one circuit to another or from one circuit to several circuits. A changing current in any of the transformer's coils causes a changing magnetic flux in the transformer's core, which generates a changing electromotive force across any additional coils wound around the same core. Without a metallic or conductive link between the two circuits, electrical energy can be exchanged between separate coils. Faraday's law of induction, developed in 1831, defines the induced voltage effect in any coil caused by a changing magnetic flux around the coil. The transformer was first developed and applied in both experimental and commercial systems by Otto Blatte, Mick Saderi, and Karel Lipski of the Austro-Hungarian Empire. The design was later developed by Lucien Gaulet, Sebastian Ferranti, and William Stanley. The induction property was discovered in the 1830s, but it wasn't until 1886 that William Stanley, working for Westinghouse, created the first reliable commercial transformer. His work was based on some crude concepts created by the Ganz Company in Hungary, as well as Lucien Gaulet and John Dixon Gibbs in England. Some questionable accounts claim that Nikola Tesla invented the transformer. The above-mentioned Europeans pioneered the field. George Westinghouse, Albert Smith, Oliver Schellenberger, and Stanley created a transformer that was inexpensive to make and simple to adapt for the ultimate application.
Hi, Assalamualaikum. My name is Muhammad Luqman Hakim bin Abdul Aziz, AA211045. So I will discuss about the relationship between inductance and transformer. So mutual inductance is where the magnetic flux of two or more inductors are linked so that voltage is induced in one coil proportional to the rate of change of current in another. A transfer is a device made of two or more inductors, one of which is powered by AC, inducing an AC voltage across the second inductor. So the mutual inductance, or the coefficient of coupling of a transformer, is a measure of the efficiency by which power is transferred from the primary to the secondary coils. So let us see the figure 5. So in figure 5, uh, the first one is high mutual inductance, which is coils close together. The second one is no mutual inductance, which is coils far apart. And the last one is little mutual inductance, which is coils at right angles. So, if the power transfer is perfect, the coefficient of coupling is 1. If there is no power transfer, the coefficient of coupling is 0. The coefficient of coupling depends on the design of the transformer. The most important factor is the position of each coil with respect to other. If the coils are one over one another and each line of flux from the primary cuts a turn in the secondary, then the coupling coefficient is very close to 1. If any flux is lost, then the coefficient of coupling is less than 1. The coefficient of coupling of typical transformer range from 0.95 to 0.99 depending on design and purpose. So now we will discuss about voltage ratio. Voltage ratio is the ratio of primary voltage to secondary voltage in a potential transformer. The ratio is usually greater than 1. The secondary voltage is stepped down to a value that is measurable by a normal voltmeter. Hence, the value shown by the voltmeter times voltage ratio will give us the voltage of the primary. The voltage ratio is the same as the turns ratio, which is Vp divided by Vs equal to NP divided by NS, where Vp is primary voltage, Vs is secondary voltage, Np is number of turns of wire in the primary, Ns is number of turns of wire in the secondary. Now, we move on to current ratio. Current ratio is the ratio of primary current to secondary current in a current transformer. The ratio is usually greater than 1. The secondary current is stepped down to a value that is measurable by a normal ammeter. Hence, the value shown by the ammeter times current ratio will give us the current in the primary. Current ratio is the inverse of the voltage ratio. That is, voltage step up in the secondary means current step down and vice versa. So the secondary does not generate power but takes it from the primary. The current step up or step down in terms of the secondary current Is, which is determined by the load resistance across the secondary voltage. The formula is Is divided by Ip equal to Vp divided by Vs. Next is transformer efficiency. A transformer does not require any moving parts to transfer energy. This means that there are no friction or windage losses associated with other electrical machines. However, transformers do suffer from other types of losses called copper losses and iron losses, but generally these are quite small. The intensity of power loss in a transformer determines its efficiency. The efficiency of a transformer is reflected in power wattage loss between the primary input and secondary output windings. Then, the resulting efficiency of a transformer is equal to the ratio of the power output of the secondary winding, Ps, to the power input of the primary winding, Pp, and is therefore high. The ideal transformer would be 100% efficient, passing all the electrical energy it receives on its primary side to its secondary side. But real transformers, on the other hand, are not 100% efficient. When operating at full load capacity, their maximum efficiency is nearer 94% to 96%, which is still quite good for an electrical device. For a transformer operating at a constant AC voltage and frequency, its efficiency can be as high as 98%. The efficiency of a transformer is given as efficiency equal to output power divided by input power multiplied by 100%. Simplify with input power minus losses divided by input power multiplied by 100%. Simplify 1 minus losses divided by input power multiplied by 100%, where input, output, and losses are all expressed in units of power. Generally, when dealing with transformers, the primary watts are called volt amps, VA, to differentiate them from the secondary watts. Then, the efficiency equation above can be modified to efficiency equal to secondary watts output divided by primary VA input.
Hello, Assalamualaikum. My name is Muhammad Afiq Saikal bin Abdul Hassani. My metric number is AA211338. Today I'm going to talk about transformer rating. Transformers are designed depending on the voltage and current that are necessary for the transformer's performance. In terms of VA, which is volt amps, that they specify on the transformer's nameplate, these are termed to as a transformer rating. The rating of a transformer can also refer to the optimum voltage and current that can be securely provided to it. The power points of transformer rating are measured in volt amperes, VE, or kilovolt amperes, kVA. This indicates that the main and second windings of the transformer are intended to resist the VA or kVA specifications imprinted on the transformer nameplate. Both direct and indirect full load rating transformer currents are normally not specified not specified, but they may be estimated using the rate VA or kVA. A transformer's rating also is determined by a rising temperature, which is determined by the transformer's losses. The temperature may be kept below acceptable levels with the correct cooling system. If the cooling system is in a good and effectively shape, so the higher the rating of the transformer will be. The rating of an electrical machine is indirectly defined mostly by losses existing in the machine for a certain cooling system. For the transformer circuit and calculation, based on the slide, I have drawn a picture of transformer circuit. Okay, based on the picture, there are a voltage, a transformer, and a resistor. Okay. For the question, a transformer has 200 primary turns and 900 secondary turns. The input voltage is 8 volts and the output current is 2 ampere when connected across a resistor. Okay, the question is, what is the output voltage? Okay, based on the question, we use the formula coil primary per coil secondary equal to voltage primary per voltage secondary. Okay. Okay, for the coil primary, the coil primary is 200, coil secondary equal to 900, while voltage primary equal to 8 voltage. Okay, for the first step is 900 multiplied with 8 voltage equal to 7200 voltage. Okay, for the voltage secondary, which is we don't know the value, multiply with 200 equal to 200 voltage secondary. Okay. 7200 voltage equal to 200 voltage secondary. Okay, we want to calculate the voltage secondary. So 7200 voltage will be divided with 200, and the result will be 36 voltage. Okay, that is the result for the question A. What is the output voltage? Okay, for the question B, which is determine the input current, we use the formula coil primary per coil secondary equal to current secondary per current primary. We have now all the value except the current primary, so we have to search for current primary. Okay, for the first step is 900 will be multiplied with 2 ampere equal to 1800 ampere. The next step is 200 will be multiplied with current primary equal to 200 current primary. For the last step we want to know the value of current primary, so 1800 will be divided with 200. Okay, the current primary will be 9 ampere. Okay, for the question C, what is the value of the resistor? Okay, we want the value of the resistor, so we will use the formula V secondary equal to current secondary and R resistor. Okay, for the voltage secondary, we have known the value, which is 36 voltage equal to current secondary, which is 2 ampere. R, we want the value of resistor. So the value of R we don't know yet. Okay. For to know the value of R, we divided 36 voltage per 2 ampere equal to 18 ohm. Okay, for the last question, question D, which is how much power is dissipated by the resistor. We use the formula P equal to I power of 2 multiplied with R resistor. Okay, I is 2 ampere, so we power the 2 with power of 2 multiplied with 80 ohm for the resistor. Okay, we have the value is 72 watt. Okay, this is the power dissipated by the resistor.
Assalamualaikum, my name is Nima Atifa Alia. So I'm going to present the application of transformers in the real world. Transformers are used in electric power transmission to allow high voltage transmission. Almost all of the world's electrical power has traveled through a succession of transformers. Transformers convert voltage from distribution cable to circuit requirements, either directly at the power line frequency or via a switch mode power supply. Besides, signal and audio transformer are used to connect amplifier stage and connect devices like microphones and record players to amplifier inputs. A balance transformer converts a signal that is ground to a signal which balances voltage to ground, such as between external and internal wires. Transformers are also used in steel manufacturing plants to provide a range of voltage for the manufacturing process. During the melting and welding of steel, high currents are necessary, but during the cooling process, lower currents are required. Transformers regulate this voltage by regulating currents inside the system. Lastly, electroplating. Electroplating typically involves the use of metal such as copper, zinc, and aluminum. Transformers are utilized to create or regulate electrical current that is employed to drive the chemical reaction. Electrolysis is fueled by the operation of transformers in chemical engineering and manufacturing operations. In a nutshell, a transformer is a passive component that transfers electrical energy from one circuit to another or numerous circuits. A changing current in any one transformer coil causes a changing magnetic flux in the core, which causes a changing electromotive force across all other coils around the same core. Without a metallic connection between the two circuits, electrical energy can be exchanged between them. The goal was achieved after conducting some research into the transformer history. We gained a better grasp of the transformer. In addition, we could identify the transformer circuit and complete the calculation. Furthermore, after conducting some research into transformer application, we are able to recognize transformer uses in the real world. I think that's all from us. Thank you.